Assalamualaikum warahmatullahi wabarakatuh, and a very good day. So this is still chapter one, but on the subtopic of the power devices. So in this lesson, so we will introduce you several devices that use in the power electronics converter, which is diode, Thyristor, or sometimes also called the SCR, silicon control rectifier, and the transistors. So in power electronics, so these are the two important features that all the power devices should have. So we will look at the usually to select the power devices. So we look at the capability of the switching speed, and the second one is the power handling capabilities. So I would like to mention that in power electronics, especially the transistors, uh, we have two function transistors. Okay, the first function is for amplifier, which has been taught during your electronic circuit, and the second function is the transistor can be operated as a switch, okay, on and off. So in power electronics, we are operating the transistors as a switch, meaning that it is on off and on off. So the first important features, which is the switching speed, is the most important features that need to be what you call look at on to actually select what is the suitable power devices used in the circuit. Okay, so this is actually some circuit, which is a very simple circuit. So actually we are using our power devices as a switch, as a switch on and off. So for example, this one, we have using a diode here. So this is AC voltage. So the simplest circuit, this is actually the simplest circuit of the power electronics, where this is AC voltage. So as you can see, we have what we call the rectified sinusoidal, where the output here is only exists during the first positive cycle only, because the diode is fault biased, while for the half negative cycle, the diode is off because reverse bias, so that's why V out is 0. So this is the simplest circuit, okay? And this is the switching characteristic. So we have what we call the ideal and also practical switch. So ideal switch meaning that we are usually use it using during our simulation work. So in the simulation work, so you can choose any transistor, any transistors. Okay, so because there is no power limit, so you can use any transistors. Okay, no power limit, no voltage block or forward current requirement, maximum forward requirement. Okay, and then the second characteristic of the ideal switch, zero turn on and zero turn off, meaning that it will immediately turn on when you want it to turn on. Okay, and the third one is there is no power dissipation or losses across the power switch. But in reality, in practical, during the construction of the hardware, this need to be taken. Okay, these 3 points need to be taken. Where the first one is that actually some devices, depending on the materials used, is actually limited in the power handling capability. Okay, so it has their rating, the maximum voltage that they can capable to block. It also has the maximum current that can flow through across the devices. And the second one is the delay turn on and off. Okay, so meaning that it has some delay during when you want the device to turn on, it has maybe a millisecond or nanosecond delay. Okay, and the third one characteristic is there is some internal resistance inside that devices. So meaning that there is some power losses. Okay, so this is the table that summarize the characteristic versus the comparison between the ideal and also the practical switch. So you can look at it. And so we go to the power device categories. So in power electronics, we categorize the device under three, which is uncontrolled, and the power device that under this category is diode. This device meaning that we cannot control. So we cannot control the diode to turn on. We cannot control, okay, on and off of the diode. It's actually depending on the circuit, whether the circuit is a forward bias condition or reverse bias condition. And the second group is the semi-control, which is the thyristor or SCR. This semi-control meaning that we can turn on the thyristor, but we cannot turn off the thyristor. To turn off the thyristor, we need to look at it's actually depending on the circuit whether it is reverse bias. And the last one is the fully controlled. So this is um, the components or the power devices that is usually used in power electronics. So we have the transistors, which is the transistor can be there are several types of transistors. So MOSFET, IGBT, GTOI, and IGCT. Fully control meaning that we can control both the on and off of the devices. So we go to the first group, which is the power diodes. Okay, so actually diodes, why is power diode? Because this shows that this diode is used for power electronics. There are also diodes that use for electronics, that what we call electronic diodes. So for power use of for the power system use, so we are using name power diode. The difference is actually is actually on the sizes and also the rating of the voltage and current. So the power diode will have higher voltage and current rating compared to the electronic diodes. So this is the symbol of the power diode. So we have anode and cathode. So we have only two terminals. Okay. So to turn on, need the circuit to be forward bias. To turn off, need the circuit to be reverse bias. So when it is forward bias, okay, so it will actually have some voltage drop across it. So around 0.2 to 3 volt. So this is the IV curve, the current voltage curve of this diode, of the diode. Okay, so when this is the condition where it is a forward bias, and when it is forward bias, there is a voltage drop here, 0.2 or 3, and the current will flow through. Okay, and then when it is reverse bias in the blocking state, so there is no current actually can flow inside. Okay, so forward bias means that the anode is positive compared to cathode, and for the reverse bias, the anode is negative compared to the cathodes. Okay, so when anode is negative compared to the cathode, so it is in the reverse bias. So the diode will behave like an open circuit, and no current will flow from cathode to anode. But there is some leaking, small leakage current that can be flow, but it can be actually ignored because very small current. Okay, but it will remain off, but until if the voltage across this diode in reverse bias is more than its limit. Okay, for example VR here. So when the voltage applied to the cathode and anode is over than its limits, so it will actually break down, and break down meaning that the diode will actually short circuit and the current will flow. Okay, so this is actually the breakdown of the diode. So the diode can no longer be used. So this is the reverse recovery. So actually this is the time of the time used for the diode to actually recover from fully. This one is actually fully on, right? Fully on because the current, and then this is fully off. So the diode needs some time to actually from turn on to completely turn off. Okay, so this time is actually we refer as a time reverse recovery. Okay, so it's actually depend on the application that you want to use, whether it is required fast TRR or slow TRR. And this is actually the example of commercial diodes. We usually have rating of the maximum voltage, maximum current, rated current, and the voltage drop here, VF, and the time reverse recovery. So usually the rated maximum voltage here is actually referring to the maximum voltage that the diode can block during the reverse blocking. Okay, and the current is actually the capability of the diode to carry the current across it during the forward bias. So this is the voltage drop when it is turned on, and this is the time that the diode need to recover from one state to another state. And this is the type of diode. So actually it depends on the application. So we have a diode that can be applied in line frequency. Usually diodes for these applications requires very slow. It's not compulsory to have a very fast TRR. Okay, so but usually diodes in this application have a very high current rating and voltage rating. And we have also diode that you can be used for fast recovery system. So in the fast recovery system, this one is usually in the where the diode is required to switch at a very fast switching frequency. And we have the third one is the Schottky. So this is a special Schottky power diodes, usually for what we call system that requires high efficiency. Okay, so the voltage drop is very limited, it is very low, 0.3, and it is used in low voltage, high current applications. Okay, the second group is a thyristor. So the thyristor itself is actually this symbol. It is actually similar to the diode, but the difference is that we have what I call the third terminal here, the gate here. So we have three terminal, anode, cathode, and gate. And for condition to turn on the SCR, we need to meet these two conditions. The first condition, okay, the device must be in forward, not forward blocking. This is one is the forward forward state, okay, not forward blocking, forward state. And the second one, the current must be a positive applied in this at this terminal. So even though you have a triggering signal going into this, but the SCR is in the reverse state, so it cannot turn on. So these two conditions must be met before the SCR can be turned on. Okay, so actually when it is these two conditions are met, so the behavior of the SCR is actually similar to the diode. Okay. So thyristor cannot be turned off, okay? It cannot be turned off, but we can turn off it, but with what I call special condition, but it is usually useless. And this is the type of the thyristor. So we have the phase control, the interpreter grade, line activated, and triac. So triac is actually we have two SCR here, as you can see, and it is frequently used in many low power applications such as juice maker, blender, and vacuum cleaner. Okay, the third group is the controllable switch, which is transistors. Most of the power devices inside this is a transistors. So these transistors is operated in saturation and cut-off mode only. Okay, so if you recall back for the transistor, we have three regions. We have saturation, cut-off, and what we call active region. So we are using on the saturation and cut-off, where saturation is actually on and the cut-off is actually turned off. No linear region operation is allowed, okay? And the traditional devices such as BJT, bipolar junction transistor, MOSFET, which is the metal oxide silicon field effect transistor, and IGBT insulated gate bipolar transistors. And this is the first transistor that we want to discuss. Is actually a very common transistor, which is called BJT, and it is invented in 1948. Okay, so collector, emitter, and base. And this device is actually a current control device. Okay, so this is not VI, is actually IV characteristic. So as you can see, this is the output side. So we have IC and VCE. So we plot the IC output and its VCE. Okay, so this is the IB characteristic, and the control comes from the IB. So that's why this device is called current control device. Okay, so depending on the value of the current, so it will plot this curve when your current is IB1, while maybe you will have this curve when IB is maybe 1, 2, 3, 4, IB5. So it depends on your value of IB, okay? And as can be shown here, so this is actually what we call the saturation region. This is where your transistor will turn on, and this one is actually what we call the cutoff region. And the center here, this is what we call the active, or sometimes we call also linear region. So we are actually operate our transistor either in saturation or cutoff only. And you also note, you also need to know that this BJT has a two type, which is PNP and NPN. Okay, so this is NPN. The current is like this. For PNP, the current is going inside to the base. The voltage rating is not very high, so you can have the transistor to the maximum is around 1 kilovolt, and the current is 400 ampere. So the limitation of this BJT is actually the gate driver is complicated. It's very complicated to design the gate driver here. That is the most major limitation of this BJT. But the advantage of BJT is actually low power losses during turn on. Okay, so you need to take note this. Okay, and this is BJT Burlington there to increase the what I call the gain. So it's not very crucial in this power electronics. Okay, the second transistor that we want to discuss is actually what we call the MOSFET. So this is the symbol of the MOSFET. So for similar to the BJT, we have N channel and P channel. So you need to know this actually N channel and the P channel symbol. And this is the terminal. Also, you need to always be remembered here. So D source and also gate here. So this device is referred as a voltage control device. Okay, and this is the output side of the transistor. So this is your IV characteristic, okay, or IV curve. So you can see that we plot the ID and versus the VDS here. So and the control unit come from VGS. So the output, the IV characteristic is depend on um, many how much value of VGS is applied. Okay, so if you have a VGS that is lower value, so we will have this characteristic. But when you increase the VGS, so you will have this characteristic. So same with the BJT, we have three regions. So we have saturation, so this is on. We have the cut-off region, which is soft, and this is what I call the active region. Okay, so This MOSFET has a very low voltage capability, so less than 500 volt, and also current is also not very high, so around 300 amperes only. But the advantage of this MOSFET is actually it can frequency up to 100 kilohertz. So this is the only device that can be switched at very high switching frequency. But the limitation is actually on uh, low power application only. Because what? Because it has very high input impedance. Okay, so very high input impedance, which is translate to the internal dynamic resistance, which is we call the RDS on. So due to that, the high internal resistance, okay, that limits the application of the MOSFET for lower application. But the advantage, another advantage of this MOSFET is actually easy gate driver construction. Okay, when we refer back here, so very easy gate driver construction. We can see here that to turn on the MOSFET and off, we need to apply positive 15 volt, and to turn off, only need to apply 0 voltage. So very easy to actually implement. Okay, so the advantage, there are two advantage of the MOSFET. The first one is the gate driver, very easy, and the second one is actually it can switch at very high switching frequency. The only limitation is due to the high internal resistance here. So due to that, it will limit the MOSFET for low power application only. Okay, and then this is the example of commercial power MOSFET. And the third one is the IGBT. So IGBT is actually the combination of MOSFET and BJT. Okay, so IGBT is actually, we can say that the son for the MOSFET and BJT. So IGBT will actually possess the good DNA from his parent, so MOSFET and BJT. So meaning that for IGBT can be said is an all-rounder winner, okay, for in a transistor, because it has a low power losses. This come from the BJT, okay, easy gate drive. This come from the MOSFET, okay, but and also due to okay, so and then the third one is actually the frequency switching. Is actually not very high, but can be considered good also. So in the medium range, okay. So it's not too, it cannot be operate at high switching frequency, but it's actually okay, suitable for most application of power electronics. So this is the example of commercial IGBT. And another one is the gate turn off thyristor. So this is the symbol is like a thyristor here. As you can see here, we have anode, cathode, and a gate. So this is the current control devices. The characteristic is similar to the SCR, but the difference is that we can actually on and off. We have two way. We can actually turn on and turn off. But actually, the turn off of this GTO is not also very easy, because normally it requires one is actually one over five of an anode cathode. For example, if the current flow inside the power circuit is 1 kiloampere, so to turn off the GTO requires a negative current of 1 over 5 of this, which is of this 1000, which is 250 volt, 250 ampere, which is not very easy to generate. Okay, and is actually, because it has the characteristic of the diode and SCR. So normally it is used in a high power rating application and so on, and the frequency is also not very high, less than 2 kilohertz. But this one, the popularity of the GTO is becoming less interest because we have IGBT, okay, and also what called the IGCT. So this is IGCT is actually similar with the what I call the symbol is similar to the GTO. Okay, the only difference is that we have this one, and then we have also a modern what I call the MCT. So this is, we can consider as a modern power devices. So this is the idealized characteristic that you need to know, or you need to actually understand. So this is the ideal, meaning that this diode, when it is turned on, the voltage is drop is zero, so the current will flow here, and this is condition where it is reverse bias, meaning that any voltage applied negative here, so the currents will still remain zero. Okay, and this is for the SCR. As you can see here, this is a forward blocking. What it meaning by forward blocking, meaning that it still block the current from flowing, even though it is a forward bias, unless it give a triggering signal is give to the SCR, so it will turn on. Okay, here, and when we turn on, the voltage drop is goes back to zero, and the current will flow, and this is actually the condition for the reverse blocking. So this is for the GTO. So GTO, it can, is a fully controlled, so we can either on and off. Similar with the BJT. So BJT is a transistor fully controlled. We can either turn on and turn off. Similar to also MOSFET, IGBT, and MCT. So all the full control can be turned on and off. Okay, so this is the what we call the arrangement of power switches, power rating versus frequency switching. So as you can see, if you want a thyristor, most of the thyristor has a power rating, very high power capability, but low switching frequency capability. MOSFET is at the end, at the lowest end, where you can switch. MOSFET usually has the highest switching frequency capability, but usually the power rating is limited to only 1 or maybe below than 10 kilowatt. Okay, the medium range is actually IGBT, GTO, IGCT. So usually this medium is actually the most suitable is actually IGBT, GTO, and IGCT. And this is also the application. So you can see most of the highest power rating used is actually for the HVDC, and that's why the thyristor mostly used in the HVDC. And MOSFET here is at least where it is used for what I call the switching power supply, okay, VCR power supply, and so on. So mostly this equipment are very low power equipment, so that's but requires a very high switching frequency. So that's why we actually can use MOSFET here. Okay, and further development, there is a technology in the development of the power device. So we call what we call the wide band gap materials. So this is not our research. This research is actually conducted by the Faculty of Science. So we are is electrical, so we only use what they have actually developed. So we have two materials, okay, for the manufacturing of the semiconductor. We call it silicon carbide and gallium nitride. So what the advantage of this is actually it increase the uh, power limitation, and also can increase the switching capability of the current device. So most of the current device are actually manufactured based on the silicon. Okay, so it is has a limitation here. But when we use the wide band gap materials such as silicon carbide and gallium nitride, so we can increase the limitation. So further development in power. So this is the reference. So thank you very much for your attention.